Okay, the next question we have here is question 3. The sketch below represents f prime x is equal to ax squared plus bx plus c, with f prime negative 5 over 3 equal to f prime 1 equal to 0 and f prime 0 equal to negative 5. Right, if we look at our sketch below, we can see we have a parabola here. But this is an f prime graph, which means that it is a derivative graph. The derivative graph here is a parabola, which means that the original graph is a cubic function. So here we're dealing with the derivative graph of a cubic function. 3.1. Write down the x coordinates of the stationary points of f. Okay, they are asking us about f, the original graph, which is the cubic function. So what will be the stationary points or the turning points of the cubic function? How do we get that from the derivative graph of the cubic function? At the bottom here I have a note that says that the x coordinates of the stationary points of the original graph are the x-intercepts of the derivative graph. So that is very important to note. So if we go back to our question, they gave us here that f prime negative 5 over 3 is equal to f prime 1, which is equal to 0. So those there are our x-intercepts. When y is equal to 0, those are our x-intercepts. So negative 5 over 3 and 1 are our x-intercepts. And our y-intercept, important to note here, when the x is 0 and they gave us an answer of negative 5 there, that's your y-intercept. So it is marked on your graph there as negative 5 over 3 and 1 as your x-intercepts of the derivative graph and 5 as your y-intercept of the derivative graph. So because they want the turning points or the stationary points of the original graph, those ones are the x-intercepts of the derivative graph. So our answers here will be x is equal to negative 5 over 3 and x is equal to 1. 3.2 now. Determine the value of x for which the gradient of the curve is negative 5, except x is equal to 0. Okay, so we can see here our graph is the same. We have our two x-intercepts there, which are negative 5 over 3 and 1. And our y-intercept is given as negative 5 there. That should be at the bottom. So let's go to our axis of symmetry that I've drawn here. If our y-intercept is negative 5 at the bottom, there will be another gradient that will be negative 5 because the parabola is symmetrical about the axis of symmetry. So down the middle of the parabola there, I've drawn my green line going down the middle. That is my axis of symmetry for the parabola. How do I get that, the value of the axis of symmetry there? You take both your x-intercepts and you add them and you divide by 2. So to get the axis of symmetry, it would be that would be equal to negative 5 over 3 plus 1 all over 2, and that will equal to negative 1/3. So my axis of symmetry, the line going down the middle of my parabola there, would be occurring at x is equal to negative 1/3. So to get the other x value where the graph would have a gradient of negative 5, I would have to move from 0, go left to my axis of symmetry, and go left again the same distance to get another point where the gradient is negative 5, just like the y-intercept there of the graph, negative 5. So to move from 0 to the axis of symmetry, we would be moving from 0 to negative 1/3. So we would be moving left 1/3 unit. So from the axis of symmetry, we need to move left again a further 1/3 units. So if we're moving a further 1/3 units from negative 1 over 3, we will end up with an answer of negative 2 over 3. So my x value, where my gradient of the curve would be negative 5 again, is x is equal to negative 2 over 3, and that would be by symmetry. 3.3. For which values of x is the graph of f increasing? So here again, they're asking you about the graph of f, but they didn't give you the graph of f, they gave you the graph of f prime x, which is the derivative graph. So here they are asking you about the original graph, which is the cubic graph. So here we need to know how to relate the cubic graph to its derivative graph, which is the parabola. Again, at the bottom there I have a note that says, for the derivative graph, everything above the x-axis is increasing in the original graph, and vice versa, which means that everything below the x-axis will be decreasing in the original graph. So they want us to find out which values of x is the graph of f increasing. So in the original graph, it would be increasing where the derivative graph is above the x-axis. So I have marked in green there the points of, or the parts of the graph that are above the x-axis. So one is on the left of -5/3, and the other one is a separate answer that's on the right of 1. So if we write our answers out, that would be x will be less than -5/3 as one answer, and my other answer would be x is greater than 1. 3.4 now, calculate the x-coordinate of the point of inflection of f. Okay, I have a note at the bottom here about the point of inflection. Just to note here again, they want the point of inflection of f, which is the original graph. How do we get that from the derivative graph? I have a note at the bottom again that says the x value of the turning point of the derivative graph is the x-coordinate of the point of inflection of the original graph. So if we apply that, we need our turning point x value of this graph, the derivative graph. But we do know what the x-coordinate there is because we did work out our axis of symmetry earlier. Our axis of symmetry, remember, goes through the x value of the turning point. It is the x value of the turning point of the parabola. So that answer was x is equal to -1/3. So because that's the turning point of the derivative graph, that will be the point of inflection of the original graph. That's why our answer is x is equal to -1/3. 3.5. If it is further given that f at 3 is equal to 24, and f is a cubic function, f of x equals ax cubed plus bx squared plus cx plus d, calculate the value of the y-intercept of f. So again, they want us to work out now the y-intercept of f, which is the original graph. But they didn't give us any information about the original graph. They gave us quite a bit of information about the derivative graph. So again, we need to relate the derivative graph to the original cubic graph. Let's start by finding the equation of the derivative graph here. So to find the equation of the parabola, we have two x-intercepts here. So we will use the x-intercept method, which is y is equal to a into x minus x1 into x minus x2, where x1 and x2 are our x-intercepts. So if we substitute those in, we'll end up with y is equal to a into x plus 5/3 into x minus 1. We need to substitute another point that's on the parabola to solve for a there. So the point we have there is the y-intercept of the graph, which is -5. So if we substitute 0 and -5 into there, where I see x, I will put 0, and where I see y, I will put -5. I will end up with -5 is equal to a into 0 plus 5/3 into 0 minus 1. If I open all that out algebraically and solve for a, I'll end up with a is equal to 3. Now I can substitute that 3 back into my second line that I have there. So I'll end up with y is equal to 3 into x plus 5/3 into x minus 1. Open all of that out using the FOIL method and then distribute the 3 into the bracket. I'll end up with my y equation for my derivative graph f prime x will be y is equal to 3x squared plus 2x minus 5. So now if we take our original f of x graph, which is given as f of x is equal to ax cubed plus bx squared plus cx plus d. And if I find the derivative of that equation, I will get f prime x is equal to 3ax squared plus 2bx plus c. But I already have the equation of my derivative graph, which is about there, y is equal to 3x squared plus 2x minus 5. If I just match those values, the coefficients of x squared will become 3a is equal to 3, the coefficients of x will become 2b is equal to 2, and my constants will become c is equal to negative 5. So I can solve for my a and my b there. 3a equals 3, so a is equal to 1. 2b is equal to 2, so b is equal to 1. And my c I already have is equal to 5. So into my f of x equation, the original there in blue, I can substitute my a, b, and c values, and I'll end up with y is equal to x cubed plus x squared minus 5x plus d. All I need to do now is substitute a point that lies on the cubic function. Then I can solve for d. So they gave me here that the point f at 3 is equal to 24. And that lies on the cubic function. So the coordinate there is 3 and 24. If I substitute 3 and 24 into this equation that I have now, wherever I see x I will put 3, and wherever I see y I will put 24. I'll end up with 24 is equal to 3 cubed plus 3 squared minus 5 into 3 plus d. And if I solve that algebraically for d by taking all the constants over, I'll end up with d is equal to 3, which is my y-intercept of f. The last one here, 3.6, determine the values of x for which f is concave up. Now, important to note here, when they want you to solve for a graph being concave up, the rule is you need to take the second derivative and make that more than 0. That's for concave up. So we have our f of x graph equation we worked out in 3.5. f of x is equal to x cubed plus x squared minus 5x plus 3. If I find the first derivative there, I'll end up with f prime x is equal to 3x squared plus 2x minus 5. And if I find the second derivative from that, I will end up with 6x plus 2 as my second derivative. I need to take that second derivative, 6x plus 2, make it greater than 0 for concave up, and solve for x. So 6x will be greater than negative 2 if I take the positive 2 over. Divide both sides by 6, and I'll end up with x is greater than negative 1 over 3 as my answer.